Operators of ships and boats must be familiar with their equipment and navigational signs on the waterways in order to successfully complete their journey. As with operators of ships and boats, wastewater treatment plant operators must be familiar with the equipment and operational signs of biological treatment processes in order to successfully treat the wastewater. The activated sludge process is a biological treatment unit that utilizes carefully controlled aerobic microorganisms suspended in wastewater to consume organic pollutants. There are three major components to an activated sludge treatment facility. They are the aeration tank, the aeration system, and the secondary clarifier. First, let's take a look at the aeration tank. Aeration tanks can be configured in a number of different fashions. They are normally constructed of concrete or steel. The sides of the aeration tank may be rounded to help promote a good mixing of the contents of the tank. Aeration tanks may be rectangular, square, round, or a continuous loop shape depending on the design of the facility. The aeration system may be either mechanical or diffused air type of system. Mechanical aerators use mixers on the surface of the water to agitate the contents of the aeration tank and to introduce dissolved oxygen into the mixed liquor. Diffused air systems use blowers that push air through diffusers in the bottom of the aeration tanks. Air diffusion systems in an aeration tank may be designed as coarse bubble or fine bubble diffusers. Some aeration systems may use a combination of mechanical mixing and diffused air. In any event, with either mechanical or diffused systems, the purpose of the aeration system is to transfer dissolved oxygen into the mixed liquor and to thoroughly mix the contents of the aeration tank. Now, let's take a look at the final major component, the clarifier. This unit will usually be constructed of concrete or steel and may be round, square, or rectangular depending on the design of the system. In the clarifier, the hungry activated sludge microorganisms are allowed to settle to the bottom while the clear, treated wastewater is decanted over effluent weirs. The settled microorganisms are then either returned to the aeration tank or disposed of as waste-activated sludge. In any event, the activated sludge is removed from the clarifier by means of the sludge collection mechanism that may utilize pumps, airlift, differential head, or a siphon mechanism to remove the activated sludge from the clarifier. It is essential for the operator to carefully control the amount of activated sludge returned and wasted from the clarifier. The amount of activated sludge returned or wasted is dependent on hydraulic and organic loading to the system. Only through proper process control testing and monitoring can the operator make the proper decisions and adjustments. Now that we have identified the major components of an activated sludge system, let's take a look at the different types and modes of activated sludge systems used. Examples include conventional activated sludge, extended aeration, contact stabilization, step feed, oxidation ditch, and sequential batch reactors. In the conventional activated sludge facility, the wastewater enters the aeration tank at one end and exits through the other. In most cases, the influent wastewater has passed through the primary treatment before entering the aeration tank. The return activated sludge usually enters the aeration tank at close to the same location as the influent wastewater. The detention time in the aeration tank is usually 4 to 8 hours, with an F to M ratio between 0.20 and 0.50. After aeration, the flow passes into the secondary clarifier, where the hungry microorganisms settle out and are either returned or wasted. The extended aeration activated sludge process is most commonly associated with package plants. The configuration of the extended aeration system is similar to the conventional activated sludge plant, except the detention time in the aeration tank is 18 to 30 hours with an F to M ratio of 0.01 to 0.07. The contact stabilization activated sludge process is different from the conventional activated sludge facility and usually utilizes two connected aeration tanks. In the first tank, known as the contact tank, the influent wastewater is introduced to the hungry microorganisms where a process known as adsorption takes place. The wastewater usually spends 30 to 60 minutes in the contact tank where the hungry microorganisms become attached to the food in the wastewater. The wastewater then passes into the clarifier where the microorganisms settle out and are returned or wasted. The return sludge is not returned to the contact tank. It is returned to the re-aeration tank where a process known as absorption takes place as the hungry microorganisms consume the food they snatched in the contact tank. The detention time in the re-aeration tank is usually 1 to 4 hours. The activated sludge mixed liquor then flows from the re-aeration tank back into the contact tank where the whole process starts over again. The typical F to M ratio for the contact stabilization process is 0.15 to 0.20. The step feed system may look very similar to a conventional activated sludge facility. In fact, with step feed, there is a great deal of flexibility and it can be operated as a conventional or even in a contact stabilization mode. When operating in the step feed mode, the influent wastewater is distributed at different locations through the course of the aeration tank. This mode of operation distributes the oxygen-demanding pollutants throughout the entire aeration tank as opposed to concentrating it at the inlet end of the tank. This helps to reduce oxygen sags in the aeration tank. Loadings and detention times for step feed are similar to conventional activated sludge. If you divert all the influent wastewater and return activated sludge to the inlet of the aeration tank, you will be operating in a conventional activated sludge mode. If you divert the return activated sludge to the tank inlet and the influent towards the latter 2/3 of the aeration tank, you are operating in the contact stabilization mode. With this flexibility, you may be able to treat peak flows or higher loadings at your facility in the contact stabilization mode. The oxidation ditch is another variation of the activated sludge process that is usually operated in the extended aeration mode. This system utilizes a continuous loop type of tank with a rotor. The rotor is a mechanical device that includes a shaft with many paddle-type blades on it. The purpose of the rotor is to mix the contents of the tank and to transfer dissolved oxygen into the mixed liquor. The sequential batch reactor is configured differently from the other processes we have looked at. In the sequential batch process, everything happens in the same tank. There is no separate final clarifier. There are usually a series of several tanks at a sequential batch type of plant, with each tank at a different stage of treatment. There are 4 basic sequences to a batch reactor. The filling mode, where the raw wastewater enters the aeration tank. In this mode, the contents of the tank may be mixed and aerated as well. The mixing and aeration mode, when the tank is full and the microorganisms feed on the pollutants in the water. In this mode, no wastewater is entering or exiting the aeration tank. The settling mode, where the tank essentially becomes a clarifier. No mixing, aeration, or filling takes place. The decanting mode, where some type of decanting device lowers into the tank and removes the treated wastewater from the aeration tank. Usually sludge is wasted from the tank in this mode as well. Ordinarily, the time for each sequence depends upon the incoming flow of the treatment facility and is controlled by some type of computer. While not all sequential batch plants operate exactly as described above, it gives you an idea as to the basic concepts of their operation. Regardless of the design and type of treatment process, it is imperative that the facility operator be familiar with the efficiency of the treatment unit and perform process control testing and monitoring. In fact, it is required by the facility NPDES permit. Examples of some of the process control information that needs to be collected or calculated and lab work that operators should perform at an activated sludge facility include influent flow and characteristics of incoming wastes, return activated sludge rates, waste activated sludge rates, dissolved oxygen, pH, temperature, mixed liquor suspended solids, mixed liquor volatile suspended solids, mean cell retention time, food to microorganism ratio, sludge settlability, dissolved oxygen uptake rates, microscopic examination of organisms, visual observation and inspection, and overall unit efficiency. When checking the influent characteristics to the activated sludge process, be sure to calculate the efficiency of the upstream treatment units. Problems upstream can lead to problems downstream. Be sure to measure all conventional parameters, including BOD and TSS. Return activated sludge rates may need to be adjusted as loadings to the facility change. Be sure to measure the TSS concentration of the return activated sludge. Using a sludge judge or similar device to monitor the depth of the sludge blanket can help you to determine when to adjust the return rates. All activated sludge plants produce excess sludge that must be wasted. Wasting of sludge needs to be based on sound process control data and calculations. Wasting rates will need adjusting as facility loadings change. In most activated sludge facilities, you can expect to produce approximately 0.2 to 0.7 pounds of activated sludge per pound of BOD removed, depending on the design of the facility and the efficiency of the upstream treatment units. One of the most important tests in an activated sludge treatment facility is the dissolved oxygen test. When checking DO levels, you should do a profile of the entire aeration tank. Generally, it is good to maintain a dissolved oxygen concentration of 2.0 milligram per liter throughout the aeration tank. Low DO levels can lead to the formation of filamentous bacteria that cause the sludge to settle poorly. If the DO becomes depleted in the aeration tank, the contents of the aeration tank will become septic. Regular microscopic examination of the activated sludge can help you to determine how many and what type of microorganisms you have. Examples of microorganisms you may normally encounter in activated sludge include protozoans, rotifers, and nematodes. The predominance of these microorganisms is usually related to the mean cell retention time. One of the most important calculations for an activated sludge facility is the food to microorganism ratio. To calculate this ratio, you need to know the amount or pounds of BOD in the influent and the pounds of volatile solids in the activated sludge system. You then simply divide the incoming food pounds by the pounds of solids in the system to get the ratio. Be sure to keep good records of all process control testing you do. You also need to keep records on maintenance and visual inspections you perform on the process. Good record keeping is a must for the professional treatment plant operator. The facility NPDES permit specifically requires operators to be familiar with the efficiency of each treatment unit. All wastewater treatment facilities produce biosolids or sludges that must be disposed. Budget monies need to be set aside for this purpose. Now, let's take a moment and quickly review the activated sludge treatment systems. Treatment systems utilize carefully controlled microorganisms to consume the pollutants in the wastewater. Systems produce excess biosolids or sludges that must be removed, treated, and properly disposed. Activated sludge systems require skilled operators that are familiar with all aspects of the treatment system and a facility NPDES permit. And now, only after the wastewater has been treated under the watchful eye of the professional wastewater treatment plant operator, can the wastewater be discharged onto the next stage in the treatment process.